Hi everyone, this is our overview of the equilibrium unit. We started with the definition of equilibrium itself. Equilibrium is when the rate of the forward and reverse reactions are equal. It has nothing to do with the concentration of reactants compared to products. It's all about the rate of the forward and reverse reactions. How fast the reactions are happening is equal. We can tell that a system has reached equilibrium when we have constant, observable, macroscopic properties. The color stops changing, the temperature stops changing, the pressure, something like that. It looks like nothing's happening, however, there's still a forward and reverse reaction. Because of that, when we write out our reactions, we're always going to put a double-headed arrow to show that we have an equilibrium. Using a balanced chemical reaction, we can apply something called the equilibrium law, where we're going to put molar concentrations, the concentration of the products, to the power of how they were balanced. It's how we're going to set up the equilibrium law to find an equilibrium constant, Kc. This constant doesn't have units, and a really big deal, especially as we get later into the unit, is don't ever include liquid water in the equilibrium law. Yes, we can have liquid water in our reaction, but don't ever include it in the equilibrium law itself. This is a little bit tricky because we could put water vapor in the equilibrium law, but not liquid water ever. We can use the equilibrium law to calculate the equilibrium constant, and that's going to tell us something about the relationship between the products and the reactants. If the constant is less than 1, the reactants are favored. That means the concentration of the reactants is greater than the concentration of the products at equilibrium. If the constant is about 1, we have about 50-50 equal concentrations approximately. If the constant is greater than 1, the products are favored. We need to be able to go from a balanced reaction to the equilibrium law, or if a question gives us the equilibrium law, we need to be able to work backward to the reaction. Plus, we need to be able to actually do the calculation to find the constant or find the concentration of a particular chemical at equilibrium. A unique style of equilibrium law question is called the icebox. This is where we set it up like this. We injected these chemicals into a reaction vessel. We mixed these chemicals together. And then we waited. We allowed the system to get to equilibrium and some change happened. And then in the end, we got to equilibrium. Icebox questions have this kind of format, not in these words, but this is the idea. We set it up like this. Initially, we waited, some change happened, and then at equilibrium, this is what we found. A couple important points about the icebox. Really watch it. A question might give you the moles and the volume separately. We're only going to put concentrations into the icebox. We can only move across the icebox on the change line. We're going to do that following mole ratios. And we're going to use the equilibrium concentrations in our equilibrium law style calculations. After working our way through the equilibrium law and the icebox, we moved on to Le Chatelier. This is different from the icebox. Le Chatelier is we were at equilibrium, we disrupted the equilibrium, and the question is always implied, how do we get back to equilibrium? The answer here is add away, remove, replace. If I add chemical D here to my reaction, I'm pushing it to the left. If I remove chemical D, I'm going to replace the ones that I took out. Add away, remove, replace. A couple important points. If we add a catalyst, that does not affect the position of the equilibrium at all. No shifting if we add a catalyst. Changing the temperature is going to change the constant. This is weird. The constant is not always constant. Changing the temperature leads to a changing constant. Any shift that pushes the reaction towards the products is going to increase the constant. Any shift toward the reactants caused by a change in temperature is going to decrease the constant. We could also get a shift by manipulating the volume or the pressure. If we decrease the volume, the pressure goes up, and we're going to get a shift towards the side with fewer gas molecules. And if we decrease the volume, the pressure goes up, we'll get a shift. However, it's worth emphasizing again, only a change in temperature will affect the constant. If we add or remove a chemical, if we change the pressure or the volume, the constant is constant. From there, we started to predict the position of equilibrium using the data booklet a lot. If the acid is physically higher on the page than the base, we call that products favored. If the acid is lower down on the page, that's reactants favored. That has a connection to this type of equilibrium reaction where acids are proton donors, bases are proton acceptors, and we have a transfer of protons. An important thing is that the acid turns into the conjugate base and they form what we call an acid-base pair. We could call it a conjugate acid-base pair. If the word conjugate is there or not, it doesn't change that the acid and the conjugate base make a pair. Likewise, the base and the conjugate acid are a pair as well. This can be connected to our work with indicators. We might be asked, okay, here's a reaction. This one doesn't have an indicator, but there might be an indicator in the reaction. After we decide if the products or the reactants are favored, we might be asked, okay, so what color is the system in the end? If we're deciding that we have products favored, then whatever version of the indicators on the product side, that's the color that we'll have. Or if it's reactants favored, it's the reactant version of the indicator. Important thing is, the first color listed in the data booklet corresponds with the acid version of the indicator, and the base version of the indicator is the second color listed. From there, we took our time with a bunch of review of these calculations from Chem 20. It's a little bit intense. And very quickly, we moved into acid equilibrium. Big deal, weak acids always have an equilibrium constant less than 1. It's always reactants favored for weak acids. Weak acids are the ones below the gray line in the data booklet, and we can do these kinds of calculations for them. If we're getting asked to solve for the equilibrium constant, the acid equilibrium constant, the acid ionization constant, that's Ka. Technically, our Ka calculations are actually icebox style problems, but by adding in this subtraction in the denominator of our calculation, we're able to avoid the icebox. We could also be asked to find the concentration of the weak acid itself, the hydronium ion concentration, the pH, or even the percent ionization. A whole range of different calculations here. Don't forget that we can always look up our Kas in the data booklet. We did a very analogous types of calculations for bases. Again, they're weak bases. Here a big thing is, questions are really often going to tell us the pH. So a conversion into pOH is very significant for our base calculations. Find the Kb of a weak base, find the concentration of a base, the concentration of the hydroxide ions, the pOH, or again, the percent ionization. After all those calculations, we found this really extra, sort of a strange way to calculate the Kb of a conjugate base. That's really important. These Kb calculations here in this base area are for weak bases. What's the Kb of the base? Using this calculation, it's to find the Kb of the conjugate base. An acid has a Ka, but it turns into a conjugate base which has a Kb. Here, this is a very strange kind of question because it is a calculation, but when we read that problem, there's no numbers. The Kb, it's the Kw divided by the Ka. The water auto-ionization constant, which we can look up in the data booklet, divided by the Ka of the weak acid itself, and we can look that up in the data book too. From there, we moved on to pH curves, where we're always graphing what's happening with the sample of a titration. This could be monoprotic, where there's only one equivalence point. If there's two vertical areas, two equivalence points, two protons were transferred, diprotic. The number of equivalence points is equal to the number of protons transferred. Sometimes we might be asked to choose an indicator. What would be a good indicator to use right there, or for either of those equivalence points down there? We'll find the pH, and then we're going to choose an indicator whose pH range, which we can find in the data booklet, includes the endpoint. We want the equivalence point, the endpoint, in that range that we can find in the data book. Finally, we ended the unit talking about buffers. Buffers are weak acids mixed with their conjugate bases, and those mixtures are resistant to pH changes. We have a buffer system set up, add a little bit of acid or add a little bit of base, and the pH is stable. It turns into Le Chatelier style problems in the end. There's going to be some shifting left or right to keep those hydronium ions, to keep their concentration stable, and then in turn the pH stays stable. We of course can overwhelm a buffer. If we put a ton of acid in there, eventually the pH is going to go down. Or if we add a lot of base, the pH will eventually increase. But the amount that we're going to add before we start to notice those changes is the buffering capacity. We covered a lot of ground in this unit. All different kinds of theoretical work, non-calculating ideas, from Le Chatelier to predicting Bronsted-Lowry equilibrium, pH curves, buffers, writing out reactions, thinking about acid-base pairs, combined with, wow, a ton of math too. All different analogous but different acid-base calculations, revisiting some of our work from Chem 20, and of course these two Old Faithful formulas over there. A really wide variety of things here in the unit. I would invite you to look back at some of the earlier videos, and I hope that helps.